What if the greatest mistake humanity ever made about the universe was assuming that it was calm, that it was finished, that it was done? What if the sky that looks so silent at night is actually in motion on a scale so vast that it reshapes what we think reality even is? That is where this story begins, not with an answer, but with a doubt. For most of human history, the universe was treated like a grand painting on a wall. People imagined the stars as fixed lights pinned to a celestial sphere, planets as clockwork pieces ticking along in perfect cycles, and the cosmos itself as something completed and eternal. Philosophers built entire worldviews on the idea that the universe simply existed unchanging outside of time, while only things on Earth were messy and evolving. That assumption felt safe. A static universe is comforting. If nothing fundamental out there ever changes, then reality is predictable. But then a question quietly surfaced. If everything is so fixed, why do we keep finding signs of motion at every scale beneath it? Atoms move planets, orbit stars, burn galaxies, rotate. Why would motion suddenly stop at the largest possible level? And if it does not stop, what does that say about the universe as a whole? This is where the idea of expansion steps in and refuses to be ignored. The claim that the universe is expanding is not just another fact to memorize. It is a direct challenge to the deepest intuition that the cosmos should be stable. Expansion says the opposite. It says that space itself is stretching, that distances between galaxies are increasing over time, and that the large-scale structure of the universe is not frozen but evolving. It turns the universe from a stage into a story. In a static cosmos, there is no meaningful before and after. In an expanding cosmos, history becomes unavoidable. Why does this change anything for us? Because once you accept that the universe is not static, you are forced to ask what it was like earlier. If galaxies are farther apart today, they must have been closer in the past. If they were closer in the past, there must have been a time when everything was far denser, hotter, and more compact than it is now. Suddenly, cosmology is no longer about describing a fixed arrangement of objects. It becomes the study of a process, an unfolding event that spans billions of years. This is why the discovery of cosmic expansion is often described as one of the greatest achievements in the history of cosmology. It did not just add a detail, it rewrote the script. Once the evidence pointed to an expanding universe completely new, theoretical doors opened. The Big Bang Theory emerges naturally from this framework not as an arbitrary idea, but as the logical consequence of running expansion backwards in time. If everything is moving apart now, then everything must once have been much closer. What happens if we follow that reasoning all the way back? We arrive at a universe that was once unimaginably dense and hot. Before this shift, many scientists, including Albert Einstein himself, tried to preserve a static universe by adjusting the mathematics of gravity. That was how deeply the static assumption was embedded in scientific thinking. The idea that the universe as a whole could be changing felt almost absurd, but the sky does not care about our comfort. Observations began to press in, showing that galaxies are not sitting still, that they are drifting apart. That space is not a rigid stage, but a flexible fabric that can stretch. What does it actually mean to say that galaxies are drifting apart? Imagine two distant galaxies separated by millions of light years. There is no engine between them, no rocket pushing them away from each other. Yet over time the distance increases. On human scales, movement requires a force acting on an object. On cosmic scales, expansion is not about objects being thrown through space. It is about space itself increasing in scale. The galaxies are like markers drawn on an inflating balloon. They are not crawling across the surface, the surface itself is stretching. This change in perspective challenges how reality is framed at the largest scales. Instead of asking where the edge of the universe is, we learn to ask how the geometry of space is evolving. Instead of thinking of time as something that simply passes, we recognize that time is tied to the history of the cosmos itself. In an expanding universe, the present moment is not just another tick on a clock. It is a slice of a larger cosmic timeline with a past that can be reconstructed and a future that can be predicted statistically. Why did this expansion idea become the foundation of modern cosmology rather than just an interesting side note? Because independent lines of evidence all began pointing in the same direction. The motion of galaxies, the leftover radiation from the early universe. The relative amounts of elements and the large-scale pattern of cosmic structure all fit naturally into the picture of an expanding cosmos. A good theory is not one that explains a single fact. A good theory is one that brings many separate facts into a single coherent story. Once the expanding universe picture took hold, the Big Bang was no longer a speculative fringe idea. It became the central narrative describing cosmic evolution from an early, hot, dense state to the vast, complex structure we see today. The expansion explains why distant galaxies are not simply hanging in space. They are carried apart by the growth of space itself. It explains why there was a time when no stars existed, and a later time when the first galaxies formed. It explains why the universe has a finite age that can in principle be measured, and yet the story is not finished. Our understanding of expansion is still evolving. Observations suggest that not only is the universe expanding, but that this expansion is accelerating, driven by something we call dark energy. That deepens the mystery rather than closing it. It means that the future of the universe is not a static fade into quiet, but a continued stretching that may eventually push distant galaxies beyond our observable horizon. The dynamic nature of the cosmos is not just a feature of the past, it will define the far future as well. So this first part of the story does one crucial thing. It breaks the illusion of stillness. It replaces the picture of a fixed universe with the idea of a living, evolving cosmos. It prepares the ground for everything that follows: the observational breakthroughs, the precise measurements, the evidence from chemistry and radiation and structure that will fill in the details. To see why any of that matters, we first have to accept a simple, startling idea. The universe is not static, it is expanding. And once that sinks in, it becomes impossible to look at the night sky the same way again. What kind of evidence would it take to convince humanity that the entire universe is expanding and not just the objects near us moving randomly? How do you go from a bold idea to proof strong enough that it forces the scientific community to rewrite its cosmic story? To answer that, you need to step into the world of Edwin Hubble and the telescopes that changed how we read the sky. By the time Hubble began his work in the early 20th century, the first cracks in the static universe idea were already forming. Astronomers were noticing fuzzy patches in the night sky. Were these just clouds of gas within our own Milky Way galaxy, or were they separate star systems, unimaginably far away? That question sounds simple, but the answer changed everything. If those patches were galaxies beyond our own, then the universe was far larger than anyone had truly grasped. Hubble was one of the people who turned that suspicion into a measurement. At Mount Wilson Observatory in California, Hubble had access to one of the most powerful telescopes of his time. This instrument did not just produce pretty pictures, it collected light so faint that human eyes alone could never see it. With it, Hubble could separate individual stars inside what many still thought were nearby nebulae. He used a special kind of star called a Cepheid variable, whose brightness rhythm acts as a distance marker. By timing how these stars brightened and dimmed, he could estimate how far away they were. The result was shocking. Some of those objects were far outside the Milky Way galaxy. They were galaxies in their own right. But distance alone was not the breakthrough. The real turning point came when Hubble asked a deeper question. If these galaxies are out there scattered through space, are they moving? And if so, how? To answer that, he needed a way to read motion from light itself. This is where the concept of redshift enters the story. When light from a distant galaxy is spread into a spectrum, its lines can shift towards the red or towards the blue end, depending on whether the galaxy is moving away from us or towards us. This effect is similar in spirit to something you have probably noticed with sound. Imagine an ambulance driving past you. As it approaches, the siren sounds higher in pitch. As it moves away, the pitch drops. This is called the Doppler effect. For light, the same principle applies. If a source of light is moving away from an observer, the wavelengths are stretched and the light appears shifted towards the red part of the spectrum. That change is what astronomers call redshift. It is not a guess. It is a measurable shift in the signature fingerprints of elements in a star or galaxy. Hubble and his collaborators carefully measured the spectra of many galaxies. Again and again they saw the same pattern. Most of the galaxies did not show blue shift, they showed red shift. They were moving away from us. At first, that alone might be interpreted as us simply sitting in a special place with everything rushing away. But Hubble did not stop there. He compared how red-shifted each galaxy was with how far away it was based on distance indicators. The pattern that emerged is now famous. The farther a galaxy was, the stronger its redshift appeared. In other words, the more distant the galaxy, the faster it seemed to be receding. This relationship was not random. It could be fit with a fairly simple straight line. The speed of recession was roughly proportional to the distance. This is what became known as Hubble law. It can be expressed in a mathematical form that links velocity to distance through a constant now called the Hubble constant. But behind that formula is a deeper conceptual message. The expansion is not about galaxies rushing away from one central explosion. It is about every large-scale region of space growing, so that larger separations grow faster than smaller ones. What does it mean for our place in the universe if every direction we look we see galaxies receding? Does that mean we are at the centre? The answer is no, and that itself is a powerful insight. In a uniformly expanding universe, any observer in any galaxy would see roughly the same pattern. Nearby galaxies move away slowly. Very distant ones move away faster. The picture is like dots on the surface of an inflating balloon. No dot is the centre of the surface, yet every dot sees all the others receding. Hubble discovery fit perfectly with that kind of geometry. The importance of Hubble work was not only in the data, but in what it did to the theoretical landscape. Before these measurements, many physicists, including Albert Einstein, had tried to force their equations of gravity to produce a static universe because they assumed that was how things had to be. When Einstein later learned of the evidence for expansion, he reportedly realized that his attempt to keep the cosmos static had been misguided. The mathematics of general relativity naturally allows for expanding or contracting solutions. The observations decided which branch nature chose. Why is redshift considered such strong evidence for expansion rather than merely for motion through space? because when astronomers mapped enough galaxies, they saw that the recession pattern is not tied to a particular region or direction. It is consistent across the sky on large scales. That uniformity matches the prediction of an expanding space model far better than any model where galaxies are simply flying apart from a local event. Additionally, the relation between speed and distance is not arbitrary. It lines up with what the expanding solutions of general relativity predict for a universe filled with matter and energy. Hubble work also did something subtle but crucial for the future of cosmology. By connecting distance to recession speed, it offered a way to estimate the age of the universe. If you imagine running the expansion backwards, you can ask how long it would take for all galaxies to converge if they had always been moving as they are now. The simplest extrapolation gives a rough timescale for the age of cosmic expansion. Early estimates were not very accurate because measurements of distances and velocities were still crude, but the method itself became a template. Refine the data, and you refine the cosmic timeline. As more precise observations were added by later generations of astronomers, Hubble's original insight was reinforced and extended. Galaxies at immense distances showed extreme redshifts, indicating that the expansion has been ongoing for billions of years. Some of these distant galaxies are seen as they were when the universe was much younger, since their light has taken a vast time to reach us. The pattern continues to support the same basic law. The cosmic fabric itself is stretching. Perhaps the most dramatic impact of Hubble discovery was psychological. It forced scientists and the public alike to stop thinking of the universe as a fixed backdrop. Instead, the cosmos became an active participant in its own story. Hubble did not invent the idea of an expanding universe from nothing. Theoretical work by people like Georges Lemaitre had already suggested that general relativity allowed for expansion, but theory without observation remains speculation. Hubble brought the sky into the argument. The evidence was painted in spectra and redshifts. This is why Hubble is remembered as a game changer rather than just another data collector. He connected the dots literally and figuratively between distance and velocity, and in doing so gave physical weight to the idea that the universe is expanding in all directions. His work shattered the static model that had seemed so natural for so long and provided the observational foundation for what would later become the Big Bang picture of cosmic history. Without those measurements, cosmology might have remained a philosophical exercise much longer. Now that the idea of expansion has observational teeth, a new set of questions becomes unavoidable. If space is stretching, what exactly is doing the stretching? How do we describe this process in terms of space-time itself rather than just as motion of objects inside it? That is where the language of general relativity and the deeper physics of expanding space enter the story. To move from noticing that galaxies are receding to understanding why requires diving into the nature of space-time and the way matter and energy shape it. That is the step the story now takes next. What does it really mean when the universe expands? Is it just galaxies flying apart through empty space like shrapnel from an explosion, or is something deeper happening to space and time themselves? To move from Hubble observational law to true understanding, the story has to step inside the physics that tells space how to behave. In the last part, the pattern was clear. Distant galaxies were red-shifted, and the farther they were, the faster they seemed to recede. That raised a simple but profound question. Are those galaxies moving through a fixed cosmic stage? Or is the stage itself changing beneath them? On everyday scales, motion always means an object changing position within space. But general relativity invites a more radical idea. Space is not a static container. It is part of a flexible space-time fabric that can stretch, curve, and evolve. So what is actually stretching when we say the universe expands? Imagine a grid drawn across the cosmos, marking equal distances everywhere. In a static universe, that grid would stay the same. Galaxies might drift across it, pulled by gravity, but the grid itself would not change. In an expanding universe, the grid is not fixed. The spacing between the grid lines grows with time. Galaxies mostly remain tied to their local grid points, yet those grid points separate from one another. The expansion is not primarily objects moving through space. It is space itself increasing in scale. How does this connect to the redshift that Hubble measured? When light travels through this stretching space-time, its wavelength is stretched along with it. A wave that left a distant galaxy with a certain wavelength arrives with a longer one, shifted towards the red end of the spectrum. This is not just a Doppler effect from motion through space. It is a cosmic redshift produced by the expansion of space during the light journey. The longer the light travels, the more stretching it experiences. That is why more distant galaxies, whose light has been in flight longer, show greater redshift. If space itself can stretch, what tells it how to do so? This is where Albert Einstein's general theory of relativity becomes central. General relativity describes gravity not as a force pulling on objects from a distance, but as the curvature of space-time caused by mass and energy. Matter tells space-time how to curve, and curved space-time tells matter how to move. On the scale of planets and stars, this curvature produces orbits and free fall. On the scale of the entire universe, the average density of matter and energy determines whether space-time as a whole expands, contracts, or remains balanced between the two. The equations that come from applying general relativity to a universe filled with matter are called the Friedmann equations. Without writing them down, their message can be stated clearly. For a realistic cosmic mixture of matter and radiation, a perfectly static solution is unstable. Small deviations tend to grow. The natural behavior is either expansion or contraction. When Hubble and others saw galaxies receding in every direction, they were witnessing the expanding branch of those solutions. The theory and the data began to speak the same language. Does this expansion mean we occupy some special central point from which everything moves away? The answer, as hinted earlier, is no. The expansion described by these equations is homogeneous and isotropic on large scales, meaning it looks the same everywhere and in every direction when averaged over many galaxies. Any observer riding with the cosmic grid would see distant galaxies receding in the same pattern that we do. The balloon analogy helps. Draw dots on the surface of a balloon and inflate it. Every dot sees all the others moving away as the surface stretches, yet no dot is the center of the surface. What about bound structures like galaxies, solar systems, or atoms? Are those also being stretched by expansion? This is a subtle but important point. Expansion is a global property of the large-scale space-time, but local regions that are held together by gravity or other forces can resist it. Within a galaxy, gravity between stars dominates over the gentle tug of expansion, so the galaxy does not get pulled apart. Within a solar system, the gravitational attraction between the star and its planets is even stronger relative to the expansion effect. Within atoms, electromagnetic forces are vastly stronger still. So while the cosmic grid expands, small-scale structures ride on that expansion without themselves being stretched. How does Hubble law emerge from this space-time picture rather than from a simple velocity field? Consider two galaxies separated by a certain cosmic distance. The expansion can be described by a scale factor that grows with time, multiplying all large distances. The rate at which that scale factor grows determines a characteristic value, the Hubble parameter. The recession speed between two galaxies is then proportional to their separation. Double the distance and you double the recession speed. That is exactly the linear relationship Hubble found, but now it is understood as a consequence of changing geometry rather than arbitrary motion. If expansion is built into the structure of space-time, how does matter and energy influence its rate? Different forms of energy affect the evolution in different ways. Ordinary matter, the kind that forms stars and planets, tends to slow expansion through its mutual gravitational attraction. Radiation has a similar effect, but behaves differently at very high densities. More intriguingly, there appears to be a form of energy associated with empty space itself, often called dark energy. This component acts not to slow expansion but to accelerate it. Observations indicate that in the current era of the universe, dark energy has become dominant on the largest scales, causing the expansion to speed up over time. This realization complicates the story but also deepens it. The universe is not just expanding. The character of that expansion changes over cosmic history as the relative importance of radiation, matter, and dark energy shifts. In the early universe, radiation dominated, later matter did, and now dark energy does. General relativity provides the framework for tracking these phases, and observations refine the values that describe them. The dynamic space-time picture is not a philosophical overlay, it is a quantitative model tested against data. Why is all this more than just abstract mathematics? Because it allows physicists to connect the behavior of light, the distribution of galaxies, and the relic radiation from the early universe into one consistent story. The same expansion that stretches wavelengths also sets the timeline for when the first atoms formed, when the first galaxies could collapse under gravity, and how large-scale structures grow over billions of years. Without the notion that space-time itself evolves, these phenomena would appear unrelated. With it, they become different chapters of one history. Seeing expansion as a property of space-time rather than a simple outward motion also changes how the future is imagined. If dark energy continues to drive accelerated expansion, then distant galaxies will eventually recede beyond our observable horizon. Their light will never reach us. The cosmic web will thin from our point of view, not because structures vanish, but because space-time stretches so rapidly that information from far regions is effectively cut off. The expanding universe is not only a story about where we came from, it is also a story about what kinds of observations will be possible in the far future. With this understanding, the earlier parts of the narrative fall into place. The idea that the universe is not static becomes more than a slogan. Hubble redshifts become more than a catalogue of galaxy motions. They are surface clues to a deeper truth. The cosmos is built from a space-time fabric whose geometry responds to matter and energy, and whose large-scale behavior is an expansion that carries galaxies along. The next steps in the story will draw on this framework to explain how the earliest elements formed, how radiation from the young universe still surrounds us, and how the large-scale structure we map today grew out of tiny initial ripples written into that expanding space-time. What kind of chemical fingerprint would an expanding universe leave behind, if any? If the cosmos really began in a hot, dense state, and then cooled as it expanded, should that history be written into the very atoms we see in stars and gas today? That is the question that turns cosmic expansion from a geometric story into a testable prediction about matter itself. Earlier, the focus was on motion and space-time, on galaxies receding and light stretching as space expands. That told us the universe is dynamic. But a dynamic universe also changes its temperature and density over time, and that has consequences for what kinds of nuclei can form. In a very early, extremely hot universe, normal atoms cannot exist. Everything is a plasma of protons, neutrons, electrons, and radiation. As the expansion proceeds, the temperature drops. There is a narrow window when it is just cool enough for light atomic nuclei to form, yet still hot and dense enough for nuclear reactions to happen efficiently. That brief era is called primordial nucleosynthesis, or more specifically, Big Bang nucleosynthesis. What actually gets made in that window? The physics is detailed, but the summary is surprisingly simple. Starting from a mixture of protons and neutrons, the universe first forms deuterium, a heavy form of hydrogen with one proton and one neutron. Deuterium then fuses into helium nuclei containing two protons and two neutrons. A small amount of lithium and beryllium can also be produced, but the conditions are not right to build significant quantities of heavier elements. The expansion is too rapid, and the density drops before complex chains of reactions can proceed. The result predicted by calculation is a universe where hydrogen and helium dominate by mass, with traces of deuterium, helium-3, and lithium-7. Why does expansion matter for this chemistry? Because the rate at which the universe cools sets the time available for nuclear reactions. If expansion were slower, nuclei could collide for longer, burning more hydrogen into helium and perhaps forming more heavy elements. If expansion were faster, many deuterium nuclei would not get fused, and both helium and heavier elements would be underproduced. The predicted ratios of light elements are therefore directly tied to how quickly the early universe expanded and what its density of matter and radiation was at that time. Change the expansion history, and you change the cosmic recipe. Now comes the key test. When astronomers look at very old, relatively pristine regions of the cosmos, do they see these predicted ratios or something else entirely? Measurements of hydrogen and helium in ancient gas clouds and low metallicity stars show that hydrogen is indeed the most abundant element in the universe, with helium making up about a quarter of the mass, very close to what Big Bang nucleosynthesis calculations predict for an expanding universe with the observed density parameters. Deuterium, which is both produced in the Big Bang and destroyed inside stars, is found in amounts that match the predicted primordial value when corrected for stellar processing. Lithium is more complicated, with some tension between theory and observation, but even there the broad picture supports an early phase of light element formation. Why is this considered such strong evidence for the Big Bang model tied to expansion? Because the element ratios are remarkably uniform across widely separated regions. Gas clouds in distant galaxies, stars in our Milky Way halo, and intergalactic material all show essentially the same primordial helium fraction once later stellar contributions are accounted for. That kind of universality is exactly what you would expect if these elements were forged in a single cosmic event when the entire observable universe was hot, dense, and nearly uniform. It is very hard to explain such consistent abundances with models in which all helium and deuterium are built solely inside stars over long periods. Could a static or non-expanding universe somehow produce the same pattern? In principle, stars do create helium by fusing hydrogen in their cores. Over immense times, they also synthesize heavier elements like carbon, oxygen, and iron. But stellar processes alone would tend to produce a much broader variety of abundances depending on star formation histories, galaxy environments, and recycling of gas. There would be no compelling reason for the same helium fraction to appear almost everywhere, especially in regions that show very little evidence of past star formation. Moreover, deuterium is destroyed in stellar interiors more easily than it is created. A universe that relies only on stars to make light nuclei has trouble preserving the observed deuterium abundance. The timing also matters. Big Bang nucleosynthesis occurs within the first few minutes after the beginning of cosmic expansion. In that short span, the conditions sweep through the temperature and density ranges needed for these specific nuclear reactions. After that window closes, the universe becomes too diffuse for such fusion to continue on a global scale. The light element ratios essentially freeze in, carried forward by the expanding gas that will eventually form galaxies, stars, and planets. What we measure today is a fossil record of those first minutes. This chemical evidence does more than just support the idea of a hot early phase. It allows cosmologists to cross-check other measurements. For example, the density of ordinary matter inferred from light element abundances can be compared with the density inferred from the cosmic microwave background and from galaxy surveys. The fact that these independent methods converge on the same values strengthens the case that the underlying expanding universe model is correct. If the expansion history were radically different, the nucleosynthesis calculations would not line up with what is seen in the sky. Think again about what that means conceptually. When you look at a star, most of the hydrogen in it likely traces back to the earliest moments of the universe, never having been processed inside a previous generation of stars. Much of the helium in that star, especially in very old stars with few heavy elements, also has a primordial origin. The ratios of these elements are not arbitrary. They were set by the competition between nuclear reaction rates and the cooling driven by expansion. In a very real sense, the chemistry of the present universe carries the signature of its dynamic past. This makes light element abundances a kind of forensic evidence. Just as a crime scene investigator reconstructs an event from subtle traces, cosmologists reconstruct the early universe from the elemental patterns left behind. There is no way to rerun the early universe in a laboratory, but the physics of nuclear reactions is well understood from experiments on Earth, and when those physics are embedded in a rapidly expanding background, the predictions match what is observed across cosmic distances. By tying together the geometry of space-time, the thermal history of the cosmos and the nuclear physics of light elements, this part of the story builds another strong pillar under the expanding universe picture. Motion and redshift told us that space is stretching. General relativity told us how matter and energy guide that stretching. Now the very composition of the universe, the overwhelming dominance of hydrogen and helium with consistent ratios everywhere we look, points back to a hot beginning in an expanding space-time. The next layer of evidence will come from an even more direct relic of that early era, the faint microwave glow that fills the sky, carrying with it a detailed image of the young universe frozen in light. What would it look like if the young universe left behind a photograph of itself, not in visible light, but in faint radiation flooding all of space? If the story of expansion and a hot beginning is real, should there be some afterglow still detectable today? A relic that has been stretched and cooled by billions of years of cosmic history? So far, the narrative has moved from the discovery of expansion to the stretching of space-time, to the light elements forged in the first few minutes. All of that points to a hot, dense, early phase. But there is an even more direct prediction, a universe that was once filled with an opaque plasma of electrons, protons, and photons should have glowed intensely in all directions. As the universe expanded and cooled, that plasma would eventually thin out and allow light to travel freely. The photons released at that moment would stream across the cosmos, their wavelengths stretched by expansion, cooling from searing energies down to microwave frequencies. That ancient light is what is called the cosmic microwave background. What kind of conditions created this background? In the early universe, before atoms could form, matter existed as a hot, ionized gas. Photons could not travel far without scattering off free electrons, so the cosmos was more like a glowing fog than a transparent space. As expansion continued, the temperature dropped. When it reached a few thousand degrees, Kelvin, electrons and protons could combine into neutral hydrogen atoms without being immediately ripped apart by energetic photons. This process, often called recombination, turned the universe from opaque to transparent on a cosmic scale. Photons that had been trapped suddenly found themselves free to travel. Those photons have been journeying ever since. Over roughly 13 billion years of expansion, their wavelengths have been stretched by a factor of about 1,000, cooling their effective temperature to just under 3 Kelvin above absolute zero. Today, this radiation appears as a nearly uniform microwave glow coming from every direction in the sky. It is not confined to one region or one galaxy. It is a property of space itself, a background that any detector sensitive to microwaves can see once local noise is removed. Why is this such a powerful piece of evidence for the expanding universe and the Big Bang picture? Because its properties match the predictions of a hot, early phase extraordinarily well. The spectrum of the cosmic microwave background is extremely close to that of a perfect blackbody, the kind of spectrum produced by matter and radiation in thermal equilibrium. Measurements from satellites such as the Cosmic Background Explorer and later missions confirm that the deviation from an ideal blackbody is tiny. That is exactly what one expects from radiation released when the whole universe was in a nearly uniform hot state and then stretched by expansion. But the background is not perfectly smooth. When instruments like the Wilkinson Microwave Anisotropy Probe and the Planck satellite mapped the sky in detail, they found tiny variations in temperature from place to place at the level of about 1 part in 100,000. Those small anisotropies carry an immense amount of information. They represent slight differences in density in the early plasma, regions that were a little bit denser or a little bit less dense than average. Over billions of years, gravity amplifies these initial ripples. Slightly denser regions attract more matter and grow into galaxies, clusters, and filaments, while slightly emptier regions become the cosmic voids. How does this connect back to the expansion story? The pattern of these temperature fluctuations is not random. When cosmologists analyze the angular distribution of the anisotropies, they see a set of characteristic peaks and troughs, a kind of acoustic pattern. These features are understood as sound waves that once propagated through the hot plasma of the early universe, oscillations in density and pressure that were frozen in at the moment of recombination. The exact shape and position of these peaks depend on the geometry of space-time, the composition of the universe, and the rate of expansion. When the data are compared with theoretical models, the conclusion is striking. An expanding universe governed by general relativity, containing roughly the observed fractions of ordinary matter, dark matter, and dark energy, reproduces the observed pattern. Could a static universe create such a background with these precise properties? it would be extraordinarily difficult. A static or steady state model would have to somehow generate a nearly perfect blackbody radiation field with a temperature of a few Kelvin present everywhere and imprint upon it a very specific spectrum of anisotropies aligned with the growth of structure we now observe. Attempts to explain the cosmic microwave background without a hot Big Bang generally run into serious conflict with the data. The background looks exactly like the cooled remnant of a once much hotter radiation field. The timing encoded in the background is also significant. From the physics of recombination and expansion, cosmologists infer that the cosmic microwave background was released when the universe was about 380,000 years old. Before that time, free electrons kept space opaque. After that time, neutral atoms allowed light to move largely unimpeded. So the background is a snapshot of the cosmos at that specific age, an image of a universe that was already expanding but still almost perfectly smooth, with only tiny seeds of the structures that would later appear. This snapshot can be thought of as a kind of cosmic blueprint. The size of the hot and cold spots on the sky, their statistical distribution, and their correlation with later structure all provide tests of the expanding model. For example, measurements of the cosmic microwave background indicate that on very large scales, the universe is close to spatially flat in its geometry. They also fix the total amount of matter and dark energy with high precision. These values can then be checked against other observations, such as the distribution of galaxies and the brightness of distant supernovae. The remarkable agreement among these independent probes supports a single consistent picture. There is another subtle but important aspect. The background helps tie together the earlier chemical story with the geometry and expansion. The abundance of light elements predicted by Big Bang nucleosynthesis depends on the density of ordinary matter in the early universe. The cosmic microwave background independently measures that density through its imprint on the anisotropy pattern. The fact that both methods point to the same value is not a coincidence. It is a sign that the same expanding space-time framework underlies both the thermal history and the nuclear history of the cosmos. Think of what this means for the overall narrative. First, galaxies and their redshifts reveal that space is stretching. Then the theory of general relativity explains how space-time can evolve under the influence of matter and energy. Light element abundances show that the early expansion was hot and dense enough to forge hydrogen and helium in specific ratios. Now the cosmic microwave background appears as the direct glow from that young phase, cooled and stretched but still carrying the imprint of that era. Each line of evidence is different in method and in detail, yet all converge on the same conclusion. The universe is expanding and has been evolving from a very different early state. The cosmic microwave background is therefore not just another data point. It is one of the strongest proofs that the expanding universe plus Big Bang picture is fundamentally correct. It gives a direct observational anchor to the idea that the cosmos once existed in a state that was smaller, denser, and hotter, and that the structures seen today grew from small initial fluctuations in that early plasma. In the next and final part of this story, the focus will shift to the largest scales of all, to maps of billions of galaxies that trace a cosmic web of filaments and voids, and to how that immense structure fits perfectly into the same expanding, evolving universe revealed by this ancient microwave light. What does the universe look like when you zoom all the way out? If the early cosmos left tiny ripples in the cosmic microwave background and set the initial mix of elements, what kind of pattern should emerge after billions of years of gravity and expansion working together on that starting point. Up to now, the story has moved from Hubble's discovery of expansion to the stretching of space-time to the forging of light elements and to the ancient glow of the cosmic microwave background that preserves a picture of the universe as a nearly smooth plasma with tiny fluctuations. Those fluctuations were the seeds. Gravity is the sculptor. Expansion is the stage on which the sculpture grows. Over time, slightly denser regions pull in more matter, become denser still, and begin to form the skeleton of what is now called the cosmic web. What exactly is this cosmic web? Imagine mapping not just a handful of galaxies, but millions, then billions, across a huge swath of space. Large surveys such as the Sloan Digital Sky Survey and others have done exactly that, measuring positions and redshifts of galaxies to build a three-dimensional map of the nearby universe. When those data are visualized, galaxies do not appear sprinkled at random. Instead, they cluster along long filaments and wall, like structures that intersect in dense knots called clusters, leaving vast underdense regions in between called voids. Why would an expanding universe naturally produce such a pattern? The answer lies in how gravity behaves on different scales. In regions where the density is slightly higher than average, the extra mass exerts a stronger gravitational pull, drawing in surrounding matter. In regions that begin slightly emptier, matter drains away toward denser neighbours, leaving them even more vacant. Over billions of years, this process amplifies the initial contrast, growing delicate variations in the early plasma into the pronounced web of filaments and voids seen today. The overall expansion of space does not erase this structure. Instead, it stretches the background while gravity fights locally to build bound systems. The key connection to earlier evidence is that the statistical pattern of this structure is not arbitrary. Computer simulations that start from the tiny fluctuations observed in the cosmic microwave background and evolve them forward in an expanding universe using the laws of gravity and fluid dynamics reproduce a cosmic web very similar to what galaxy surveys reveal. The size of typical filaments, the abundance of clusters, and the characteristic emptiness of voids all match the predictions of a universe that has been expanding for billions of years under the influence of dark matter, ordinary matter, and dark energy. Could a cosmos that is not expanding somehow generate the same distribution of structure? It would be extremely difficult. The growth of fluctuations depends sensitively on how fast the background density drops, which is controlled by the expansion rate. In a static model, gravitational collapse would proceed very differently, often too quickly, or in ways that fail to match the observed balance between clustered and unclustered regions. The observed large-scale structure is therefore another independent check that the same expansion history inferred from redshifts, light elements, and the cosmic microwave background also governs the growth of galaxies. Void regions in particular carry an important clue. These are not simply empty holes. They are places where expansion has effectively outpaced gravitational clumping on local scales because there was not enough matter to reverse the flow. As the universe expands, matter falls into filaments and clusters, leaving behind underdense patches that continue to stretch. The existence and size distribution of these voids fit comfortably within the expanding universe paradigm. They are the negative spaces carved out by the same processes that build the bright nodes of the web. When all of these observations are viewed together, a remarkably coherent picture emerges. Hubble law shows that distant galaxies recede, with speeds proportional to distance, pointing to expansion. The general relativity framework explains how space-time itself can stretch and how matter and energy influence that stretching. The relative amounts of hydrogen, helium, and other light elements record the conditions and expansion rate in the first minutes. The cosmic microwave background provides a snapshot of the universe when it was only hundreds of thousands of years old, with tiny density ripples written into the plasma. The present-day cosmic web of galaxies is the grown-up version of those ripples, shaped over billions of years by gravity against the backdrop of an expanding space-time. This convergence of independent lines of evidence is why cosmologists describe the expanding universe model with the Big Bang framework as robust. Each piece alone might be interpreted in multiple ways, but together they interlock. Change the expansion rate too much, and the light element abundances no longer match. Alter the composition of matter and energy arbitrarily, and the pattern of cosmic microwave background anisotropies and large-scale structure fall out of alignment. The success of the model is not that it explains one observation neatly, but that it explains many very different observations with a single underlying story.